Hey everyone, my name is Max Leamy, and today I'll be presenting the magnetic field of a bar magnet experiment. As an introduction, in the lab we used a bar magnet to model a magnetic dipole and used a cell phone with a magnetometer to measure the magnetic fields at several points in space to observe the relationship between distance from the magnetic dipole and the magnitude of the magnetic field. For the results, the power that the distance is raised to in the relationship formula was found to be negative 2.7724, and the magnitude of the magnetic dipole was found to be 1.3785 amps meters squared. For the physics concepts in the experiment, the Biot-Savart law, relationship between magnitude of the magnetic field of a bar magnet to the K constant and distance r from the magnet, and the relationship between the recorded data and distance in K were used. The Biot-Savart law was used to calculate the magnetic field at various points in space due to the bar magnet. The bottom formula was used when solving for the magnetic dipole mu, and the relationship between the recorded data and r and k was used to find the values to plug into the other two equations. For the experiment, we assumed a bar magnet acted as a magnetic dipole. The system of the experiment was the bar magnet, and the surroundings of the experiment was everything surrounding the bar magnet. The initial conditions of the experiment was the bar magnet was placed at the end of a meter stick, and the magnetometer was downloaded onto the phone. For the first part of the experiment, we first determined the position of the magnetometer on the phone and found the on-axis distances from the bar magnet readings for several magnitudes of the magnetic field. We then plotted these values as a function of natural log of magnitude of the magnetic field versus natural log of the distance from the bar magnet. We then related our trend line to the equation relating our data below the graph. The value of n is the slope of the graph, negative 2.7724. The value of natural log of k constant is the y-intercept of the graph, negative 15.024. We then also took measurements for the off-axis magnetic field of the bar magnet. The results are shown below. For the experiment observations, the underlined statements were proven true by the experiment. When the magnetometer is far away from the magnet, it does measure a near zero magnetic field in the x direction. For the second statement, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field actually increases rather than decreases. For the third statement, the Earth's gravitational field also influences the magnetometer readings, so it is important to line up the magnetometer towards the north. And for the fourth statement, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field does increase. Using the equation for the trend line of our data from the experiment, I first found the values of n and r. I then set the equation for the magnetic field on axis for the bar magnet to the formula for the magnitude of the magnetic field that relates k and r. I then plugged in the values of k, the constant mu 0 over 4 pi, and n to the equation to solve for the magnetic dipole of the bar magnet, which I calculated as 1.378 amps meters squared. For the coding demonstration, I first defined the constant mu 0 over 4 pi, created a magnet in space, and inserted the magnetic moment I calculated earlier. I also designed a function to calculate the magnitude of a magnetic field due to the bar magnet at a point in space. I then used the average distance from calculating magnetic field perpendicular to the bar magnet to design 6 observation locations to calculate the magnetic field arrows on axis and off axis from the bar magnet. I also found the magnetic field 45 degrees from the axis to display on the simulation. Here are my results of the simulation. When comparing the off-axis field magnitudes for the simulation and experiment, the simulation's magnitude for the off-axis field was 1.789 times 10 to the negative fifth amps per meter, while the experiment's result was 7.52978 times 10 to the negative fifth amps per meter. Experimentally, we measured a much larger off-axis field magnitude than the experiment, or than the simulation. Some sources of error in the experiment could be due to our model assumptions, as well as possible sources of error due to poor identification of magnetometer position on the cell phone, moving the phone imprecisely and gathering incorrect measurements, and there may have also been other magnetic fields influencing the phone's magnetometer during data collection. For the what if and what does it mean questions, if we hadn't compensated for magnetic north, the Earth's magnetic field would have interfered with the data collection during the experiment and would have skewed the data, causing even more discrepancy between the experimental data and coding simulation. I also expect the value for the magnitude of the magnetic field of the on-axis and off-axis calculations to increase if two identical magnets were stuck together. The magnetic dipole magnitude would increase. Thank you so much.